the tips of our noses to the farthest flung galaxies. This analogy captures the magnificence of LIGO. It's about much more than proving a scientific prediction. LIGO enables us to perceive the physical universe and understand reality on a new level. Like photons, gravitational waves travel at the speed of light as they ripple across space-time. Their signals are all around us. By listening for gravitational waves with some of the most sensitive instruments ever built, scientists are recording tremors of distant violent events. The formation of black holes, supernova explosions, and potentially exotic phenomena we haven't discovered yet. So what are gravitational waves? What causes them? And why is LIGO's ability to detect them already transforming our understanding of the universe? I'm Alex McCohen, and you're watching Astrum. Join me today as we learn about gravitational waves, unpack the groundbreaking technology behind LIGO, and anticipate some of the stunning developments that lie around the corner. Gravitational waves are one of the stranger implications of Albert Einstein's general theory of relativity. As we've covered previously, space-time is a model that combines the three dimensions of space and the fourth dimension of time into a single manifold. All objects with mass create curvature in space-time, and objects with a lot of mass create a lot of curvature, which we experience as gravity. A simple way to visualize this is to think of a pool ball resting on an elastic surface and a bowling ball resting on that same surface. The more massive bowling ball will create more curvature. As objects move across space-time, that curvature changes position with them. One of the amazing consequences is that when objects of a certain mass accelerate, they can send ripples across space-time as gravitational energy. While this requires a special set of conditions, namely, a very massive object undergoing acceleration, such a cataclysmic event would send ripples or gravitational waves outward at the speed of light. Think of them like ripples on a pond, but instead of water, they travel through the fabric of space-time in all directions. As in the pond analogy, these disturbances become weaker as they radiate outward. To an observer, the distance between objects would appear to expand and shrink as the gravitational wave passes. Mind-boggling to imagine. Yet, although Einstein predicted the existence of gravitational waves, he was pessimistic about our chances of ever detecting them. He thought that these disturbances would be so small as to escape our ability to measure them. And who could blame him? Many of the changes in distance that LIGO seeks to measure are 1/10,000th the length of a proton. Yes, you heard that correctly. 10,000 times smaller than a single proton. And yet these signals would come encoded with all kinds of information about their origins, when they originated, how far they traveled, and what kind of event produced them. This is where LIGO comes in. It consists of two observatories funded by the United States National Science Foundation and operated by MIT and Caltech. Among its driving forces are renowned physicists Kip Thorne, Raina Weiss, and Barry Barish, all of whom shared the 2017 Nobel Prize for their decisive contributions to the detection of gravitational waves. LIGO is essentially a large-scale and very sensitive interferometer, an invention that's been around since the 1880s. An interferometer essentially measures what happens when light waves are combined from two or more sources. For example, you could use an interferometer to test whether light travels at different speeds through different substances, such as through air or water. Even a subtle difference in speed will produce an interference pattern when the light waves combine, much like what happens when two ripples on a pond intersect. If the peak of one ripple hits the value of a second ripple, they will subtract from each other, producing a flat surface. However, if the peaks line up exactly, it means the waves are in phase and add to each other. This is essentially what the interferometer measures with light. By seeing how in or out of phase two light waves are, an observer can infer the relative speed of the waves. And the larger and more powerful the interferometer, the more sensitive it is. Here's how it works. LIGO has two observatories located in Hanford, Washington, and Livingston, Louisiana. Why two? Well, you need at least two detection sites to triangulate where the signals are coming from. Each observatory continuously fires a powerful laser at a beam splitter positioned at a 45.8 degrees angle. The laser beam has to operate at around 750 kDq, powerful enough to vaporize you completely if you got in its path. The splitter then splits the laser beam perpendicularly. The light in each arm travels down a 4-kilometer vacuum cavity with a mirror at the end of it. The beams then bounce between this mirror and a recycling mirror at the other end nearly 300 times, increasing the distance from 4 to 1,200 kilometers. Remember what we said with interferometers. Bigger is better. After completing nearly 300 trips, the laser beams combine at the beam splitter and head to a photodiode, which is a light-sensitive semiconductor. If undisturbed, the beams will be in phase, meaning their frequencies will subtract each other and 000709. No light will arrive at the photodiode. But if there's a gravitational wave, the distance each beam travels will be slightly different and they'll be out of phase. The photodiode will pick up a signal indicating the presence of a gravitational wave. Now this is how it works in a perfect world. But in reality, the interferometer is constantly picking up noise. To minimize this, LIGO uses incredibly smooth 40-kilometer mirrors suspended by silica threads. Any particles in the interferometer's arms are also a problem, which is why LIGO pumps the air from its vacuum chambers to 1/1,000,000th of atmospheric pressure. But there's another problem. At these minuscule levels, even quantum mechanics are a nuisance because they introduce randomness into photon behavior. LIGO mitigates this with an optical cavity which squeezes the light. This squeezing minimizes the light phase's noise and squeezes it into amplitude noise, which the interferometer doesn't measure. Other words, the quantum randomness will show up more in the height of the waves. Quantum randomness is a fact of life. It can't be eliminated, but it can be shifted. Much as you might move clutter from your bedroom floor to your closet, the chaos isn't gone, just out of sight for the moment. Plus, the goal isn't to eliminate noise completely, but to get the best signal-to-noise ratio possible. That's a pretty good overview of how LIGO works. So, what has it discovered? As I mentioned earlier, LIGO detected its first signal in 2015, named GW150914. Scientists studied the data and learned that it was caused by the merger of two black holes about 1.66 billion light-years away. These black holes, which were 29 and 36 solar masses, became a binary and spiraled around each other until they merged and released a blast in the final 20 milliseconds that was so powerful. Now, get ready for this number because this is what the scientists actually think. It contained 50 times the combined light power of every star in the observable universe. At the risk of sounding crude, that is nuts. I've read this fact many times over, and I still cannot comprehend what it means. Yet after traveling for 1.66 billion years and finally reaching LIGO, the disturbance was so faint it moved LIGO's 4-kilometer arm 1,000th of the width of a proton. To visualize this, imagine the distance between us and Proxima Centauri and changing it the width of a human hair. That is the level of precision LIGO was able to detect. If that's not one of the most astonishing feats in human history, I don't know what is. And this was just the first gravitational wave LIGO detected. The second detection occurred 3 months later in December 2015. That signal also came from a black hole merger which took place 1.4 billion light-years away. Over its initial 3 runs, LIGO recorded more than 80 black hole merges. And in August 2017, it detected the merger of 2 neutron stars named GW0817. This signal was notable for being the first gravitational wave to be cooperated by electromagnetic observations from 70 observatories across the planet. This was a breakthrough not only in gravitational wave detection, but in multi-messenger astronomy. It turns out LIGO was just warming up during these 3 runs. As of May 2023, LIGO has begun its 4th run with better sensitivity than ever. After its latest round of upgrades, which kept LIGO offline for 3 years, the observatories now have more reflective mirrors, better mirror suspension, and improved light squeezing with lower quantum uncertainty. And this time, LIGO also has the support of Kagura, a new interferometer observatory in Haida, Japan. Kagura is located underground, making it the world's first subterranean gravitational wave observatory, and also the first to use cryogenic mirrors. During an engineering run on the 18th of May, LIGO scientists say they already received a signal that was possibly caused by a neutron star being swallowed by a black hole. We'll have to wait a while for confirmation, but if these early results are any indication, LIGO is about to blow the doors of our understanding of gravitational wave-generating phenomena. So, what other developments lie ahead? India is preparing a collaborative project called LIGO India, or Indigo, which will help LIGO triangulate better location data. In 2027 to 2028, LIGO will implement its LIGO Voyager upgrade, which will achieve higher sensitivity with 4 times heavier mirrors and higher frequency lasers. And in the more distant future, a 3rd-generation facility has been proposed called Cosmic Explorer. This facility would feature 2 new observatories with arms spanning 40 kilometers and 20 kilometers, respectively. Remember, with interferometers, bigger is better. But the proposal that really excites me is the Laser Interferometer Space Antenna, or LISA. This would be the first space-based gravitational wave observatory, which would utilize 3 spacecraft in a 2.5 million kilometers long configuration. This interferometer would be so big and so precise, scientists hope it would be adept at uncovering exotic and theoretical sources of gravitational waves, such as cosmic strings and other speculative phenomena. In theory, it could help us stare directly into the fabric of reality. With a planned launch date of 2037, we're still over a decade away, but it's never too early to start counting the years. So, there you have it, an overview of LIGO and how scientists are using gravitational waves to better understand the universe. They give us evidence of extremely remote and ancient phenomena that cannot be measured by other means. And they can be a secondary way to measure observations made by other instruments like the Webb telescope or Hubble. In time, this revolutionary field should allow us to understand the nature of our universe, its history, and even its future. I hope you found this episode as fascinating as I have. Tune into the universe with the right equipment, and you will hear it humming no matter where you look in the sky. Of course, it's not possible for sound to travel in a vacuum of space. Instead, we are talking about the hum of gravitational waves. You might already be familiar with a similar signal discovered decades ago. It's called the cosmic microwave background, and it is the afterglow of the Big Bang. This glow of microwave light was a groundbreaking discovery. It was the smoking gun that solidified the Big Bang's place as the leading theory of our universe's beginning. Yet this light signal had a glaring weakness. Despite it being the earliest light of our universe, it was emitted almost 400,000 years after the Big Bang. If we want to go back earlier, we will need a background signal made not of light, but of the ripples of the fabric of space-time. In 2023, astronomers at the Nanograph collaboration have announced that by using a clever trick, they may have detected just that. Using exotic stars as a galactic-size gravitational wave detector, they measured the faint hum of space-time itself. This hum of gravitational waves might just be the reverberations of the very creation of our universe. I'm Alex McCollin, and you're watching Astrum. Join me today as we learn about the secrets of gargantuan gravitational waves and the ingenious new method astronomers have used to detect them. In a previous episode, we covered the LIGO detector and how it uses lasers to precisely measure the minuscule changes in the length of a tunnel caused by gravitational waves passing through. These gravitational waves stretch and squish space-time, causing changes in the time it takes for light to travel from one end of the tunnel to the other. But detectors like LIGO are only sensitive to a specific kind of gravitational waves. Like light waves and sound waves, gravitational waves can come in different frequencies. And LIGO is only able to listen in to one part of this spectrum, the high frequencies. That's when these binaries are spiraling in on each other rapidly, completing hundreds of rotations per second before colliding in a great bang. But that is also why LIGO cannot listen in on the much earlier stages of these binaries when the objects are orbiting each other at a much greater distance. Because these orbits are much slower, the gravitational waves they produce are of a lower frequency and energy. So you could say, rather than a great bang, they give off a faint hum, combining into one collective signal. Bigger black holes give greater contributions to this signal. The loudest contributors would consist of pairs of supermassive black holes, the kind you'd find at the center of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are expected to be rare because they only form when something truly spectacular happens. The merger of two galaxies. When galaxies merge, because of the vast amounts of empty interstellar space in them, they mostly phase through each other. Very few, if any, actual collisions of stars or planets happen. But the stars gravitationally attract one another and merge into one collective galaxy. And the nuclei of these galaxies, the supermassive black holes, form binaries that continue orbiting one another long after the galaxy merger appears to be complete. It's these remnants of galaxy merges that we would hear most strongly in the ultra-low frequency range, specifically around the nanohertz range. Yet, just like how the human ear cannot hear sounds with ultra-low frequencies, LIGO is deaf to this cosmic cacophony. If we could listen in, we would gain new insight into galaxy merges and black holes. But that's not all. One of the most exciting things about the gravitational wave background is that it is a window to the very first moments of our universe's existence. Let's quickly recap what we know about the cosmic microwave background. This microwave light is the earliest light that we can detect, because for the first 400,000 years, the universe was opaque to light. What does it mean for the universe to be opaque? Initially, the universe was far too hot for neutral matter to exist. Electrons and protons were unable to bind together and form neutral atoms simply because they had too much energy. This state of matter is called plasma, the same stuff that stars are made of. And the universe was filled with it. Light gets trapped in plasma, unable to move through space without bumping into the charged electrons and protons being continuously absorbed and emitted. But once the universe expanded and cooled down enough for the protons and electrons to coalesce into neutral hydrogen and helium atoms, it suddenly became transparent. The light was finally freed. This light was then stretched by the expansion of the universe until it redshifted into microwave light. This is why the cosmic microwave background is the earliest light of the universe. But gravitational waves are not made of light. They are made of space-time itself. Plasma is no obstacle to them. To gravitational waves, the universe has been transparent from almost the very instant of the Big Bang itself. They can penetrate past this plasma barrier and offer us a glimpse of the very first moments of the universe's creation. Because these primordial gravitational waves have been traveling for so long, even if they were originally produced with a high frequency, They would be greatly stretched by the expansion of space-time. They would be redshifted into ultra-low-frequency gravitational waves, the same kind that would come from black hole binaries. Together, these multiple sources will give us a so-called stochastic gravitational wave background existing over a range of low frequencies. How can astronomers retrieve this treasure trove of information about black holes, the Big Bang, and more? Can we build a better LIGO and detect how the Earth is bobbing up and down in these gargantuan gravitational waves? Well, LIGO works by sending two beams of light being sent along perpendicular tunnel arms. The beams are reflected by mirrors at the ends of each of those tunnels, and they return to the starting point and are compared with each other. This is so that if space-time gets distorted along one direction, the information from the other direction can be used to get a sense of how much it has changed. Unfortunately, if we were to design a new LIGO to detect these gravitational waves, we would need to have tunnel arms that are much larger than anything we could build on Earth. This is because the frequency of a wave is inversely proportional to its wavelength. Ultra-low frequency waves have an ultra-long wavelength and would require us to look at changes over a much greater distance to notice the effects of these gravitational waves. For nanohertz waves, that is one full fluctuation taking 1 billion seconds. A quick calculation. Wavelength equals speed of wave over frequency tells us that the wavelength would be around 10 or 17 desmers. For a sense of scale, the distance between the Earth and the Sun, or an astronomical unit, is 10 out of 11 mers. A light year is around 10 or 16 mers. The wavelengths we are discussing are tens of light years long. Clearly, we cannot build anything suitable for this task on Earth or even in Oasis. The solar system. We need to go beyond our stellar neighborhood. But rather than wait for humanity to ascend beyond the confines of our solar system and become a space-faring civilization, astronomers at NANOG have used a clever trick. You may recall our recent episode on pulsars and how we discussed that these ultra-dense neutron stars are able to spin with remarkable stability. They emit light along their poles, and we can detect the pulses that we receive as those vast beams of light swoop around and hit the Earth again and again. These pulses come with such precise certainty that they are used as clocks of the cosmos, able to keep time across vast distances. Therefore, we can use already identified pulsars to supply us with reliable signals from thousands of light years away. The pulsars are like the mirrors at the end of the LIGO arms, but rather than sending us back a signal we send across, they are generating their own. Nanograph have cleverly concocted an imaginary interferometer that stretches for thousands of light years. And all we need to use it are the good old radio telescopes that we've been using for decades. But our calculations will only be as good as our observations. When choosing pulsars to observe, we need to make sure that they are suitable for the task. The best candidates are hand-picked and added to a group called a pulsar timing array. For nanograph, they have made use of 68 pulsars, which were chosen for the following special properties. They had to be spread all across the sky, so we can figure out how these massive gravitational waves are affecting space-time in all directions. Also, they had to be millisecond pulsars, which means they complete millions of rotations per second. In our recent pulsar video, we talked about how these fast-spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses. In fact, their stability even rivals that of some atomic clocks. We could not ask for better timekeepers to be dotted across space and time. This regularity means that we can take measurements of the time their pulses arrive, and continue taking these measurements over multiple years to see if there are any changes happening. Of course, the times of arrival can vary due to all sorts of factors such as the change in distance between the Earth and the pulsar, as both objects continue moving around space. But we can take this into account quite easily. However, there are less predictable factors, such as random fluctuations in the interstellar gas the light is traveling through, causing delays that aren't coming from the stretching of space-time. How do we get rid of the random noise in our data from pulsars located thousands of light-years away? With statistics, we can isolate the gravitational wave background from the random noise by considering correlations between pairs of pulsars in the pulsar timing array. Just like LIGO, one tunnel isn't sufficient. We need 2 pulsars on each end of our imaginary tunnels. If similar fluctuations show up with 2 pulsars, it is unlikely that the random noise aligned in such a way to make it appear by chance that they are acting in unison. It is far more likely that there is a common cause underlying both those fluctuations, such as the possibility that the photons from the 2 pulsars are riding the same gravitational wave that are washing by them both. We can then relate these correlations of pulsar pairs with the angular distance in the sky. If there is no gravitational wave background, we expect there to be no correlation and the graph to show a straight line at 0. However, if the data shows a special curve called a Heelings and Downs curve that would indicate that a gravitational wave background is responsible for the variances. That's what nanograph have succeeded in doing. On the 28th of June 2023, based on over 15 years of continuous observations of their 68 pulsars, they announced strong evidence for the gravitational wave background. This is the graph we've been waiting for. This is a hallmark of gravitational waves which stretch along one direction and squish in the perpendicular direction. This is exactly what we are seeing with this graph. When pulsars are separated at right angles, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data appear quite large, but the researchers have calculated that the data shows that the existence of a gravitational wave background is statistically significant at the 3 sigma level. This means that there's only a 1 in 1,000 chance that this is a false alarm, and that this data was the result of mere chance. In physics, the 5 sigma level is considered the gold standard for a discovery, but 3 sigma is still very strong evidence. As they collect and analyze more data, astronomers will be able to reduce those error bars and finally announce an official discovery. So, what secrets does this gravitational wave background reveal? While we cannot pick apart the sources of the collective noise just yet, we hope that these techniques will eventually allow us to listen in to specific supermassive black hole binaries and figure out what the signal can tell us about the creation of the universe. Until then, astronomers will continue to use their galaxy-size detector to calculate how we are bobbing up and down in the turbulent sea of space. Have you heard about nanograph before? What secrets do you think gravitational waves could reveal? Let us know in the comments below. Every year since 2018, astronomers have spotted a mysterious blue flash in the sky. It is one of the brightest phenomena in the universe. An explosion that makes the average supernova look like a faintly lit candle in the distance. Some have been spotted closer to us and others billions of light years away. They look similar enough to one another, but no one knows what they are or what causes them. Through rigorous observation and analysis, astronomers began decoding a pattern and formulating a tentative but plausible theory. Until in 2023, they saw something that left them completely baffled. These explosions are called luminous, fast blue optical transients, and there's simply nothing else like them out there. I'm Alex McCohen, and you're watching Astram. Join me today as we dive into the mystery of space's brightest explosions, how they were discovered, and why they keep stumping scientists again and again. Being such a recently discovered event, the data we have on luminous fast blue optical transients, or LF-BOTs for short, is minimal. The first LF-BOT ever detected was identified just 6 years ago in 2018, and we've only witnessed a handful of them since. As so little is known about them, it makes agreeing on a universal definition a little tricky. For now, what scientists do all agree on are some common characteristics these LF bots seem to share. So far, they all display a predominantly blue emission, very high optical luminosity, and being bright in X-rays, ultraviolets, and radio waves. They are also very fast, as their name indicates. LF bots go off like a cosmic camera flash. They reach peak brightness and then dim very rapidly, usually in the space of hours or days. As you might know, a supernova follows the same pattern of brightening and then dimming. But this dimming takes weeks or months. This short-lived nature of LF bots makes them difficult to spot and study. So, how did we manage to capture such an elusive event? NASA's Atlas HKO telescope in Hawaii is part of an early asteroid impact warning system that scans the entire sky several times a night for moving objects. On the 16th of June 2018, Atlas HKO was performing its routine scan when it captured something very unusual, a flash 100 times brighter than a regular supernova that disappeared within days. The scramble was on. Scientists immediately started analyzing the data to understand what they'd seen. They pinpointed the explosion as coming from the Hercules constellation, some 180 million light-years away. Officially designated at 2018 Cow, the event was affectionately nicknamed the Cow after the last 3 letters in its name. Once located, it was quickly classified as a Type 1b supernova. This kind of supernova, also known as a core collapse explosion, is formed when massive stars collapse under their own gravity. But something about this particular explosion didn't quite fit. When taking a closer look at the Cow's emission spectrum, it didn't look very typical for a Type 1b supernova. It had unusually broad emission lines and very weak helium lines. Scientists thought it appeared more reminiscent of a Type 1 CBL supernova, and so was quickly reclassified. However, the more scientists pored over the data, the more surprised they were by what they found. Whatever this explosion was, it started to look less and less like a supernova. At least not the kind of supernova we'd expect. For starters, it appeared out of nowhere. This blast went from inactive to peak luminosity in just a few days. Like we mentioned earlier, supernovae usually take a few months to reach their brightest and dim again at a similar pace. Not only that, it was registered to be 10 to 100 times brighter than an ordinary supernova. Also, everything about the way it exploded was wrong. When supernovae explode, they tend to release their energy in a spherical shape. We know now that the shock wave sent out after a supernova can be aspherical, due to the presence of strong magnetic fields, which can distort the shape of the initial blast. However, upon closer inspection, this mystery explosion did not even explode spherically. The researchers themselves called it the most aspherical explosion ever seen. Soon enough, other theories were being put forward. Some thought the Cow could be a monster black hole, shedding a passing star. Others suggested it was a supernova that gave birth to a black hole, or a neutron star. But let's step back for a moment. It's really hard to draw any conclusions when you only have one of something. As the saying goes, once is an anomaly, twice is a coincidence, and 3 times is a pattern. What researchers really needed was a bigger sample size, more instances of this kind of explosion, so they could compare observations and deduce any patterns that might arise. Luckily, it didn't take long for scientists to get their eyes on a second similar explosion. A few months later, in September 2018, the cosmic camera flashed again and again for a third time in 2020. Keeping in the tradition of pulling animal nicknames from the last 3 letters of their official names, we had the beginnings of our LF bot zodiac. The cow was joined by the koala and the camel. And just like that, they had data on 3 separate LF bot events. They could start hunting for patterns. When analyzing the cow, koala, and camel, one of the first things that stood out to researchers was the location of these events. Even though they all happened in different parts of the universe, each blast was registered as coming from inside the spiral arm of a galaxy. At first, this information emboldened the initial theory that LF-bots were just a type of core collapse supernova. Let me explain why. The kind of star that causes a core collapse supernova is a massive star, one of the biggest types of stars you can get. And as you know, the bigger the star, the shorter its lifespan. This means that these stars don't get the chance to travel very far before they die. It would make sense then that their supernova occur very close to the star cluster where they were born. And what part of the galaxy is known for having such clusters? Yep, the spiral arms, the exact place we saw all three LF-bots. But just as researchers seem to be making progress, something happened that caught them completely off guard again. Like the Atlas HKO in Hawaii, the Tuiki Transient Facility is a very wide-angle ground-based camera that scans the whole northern sky every 2 days. In 2022, it detected another similar explosion, except after